Good morning, everybody, and welcome to Astronomy 100. Today is September 14th. We are in week 5, and we are approaching our first exam. And we're basically covering a lot of materials. So I'm hoping that you guys, the ones who are not here, and I know that at least some of you are keeping up with work, so hopefully you guys are on top of it. If you have difficulty again, please let me know, and hopefully we'll work out through all of those issues. Now, this week, we have, again, quite a bit of materials that we need to go through. So what I'm planning to do is actually review this week's objectives, and also the homework, basically assignment. These are the topics that we need to cover this week. There is an issue with the exam. I really need to go through all of those, or the quiz, actually, it's not an exam, I should say. I need to go through them and regrade them, because what happens is Canvas has defaults to this grading system, for example, where you have multiple matchings. And if you don't get them all right, it gives you no credit whatsoever. But I have to go in there and override that one, because a lot of you apparently were getting a lot of those matches correctly, except with 1 or 2. So you need to get partial credit for those assignments. Also, sometimes the answer is kind of correct, not exactly the correct answer that you were asked. But for example, asking you about how the density is measured in the metric system. And of course, the correct answer is a kilogram per cubic meter in the metric system. That is the correct answer. But some of you chose the grams per cubic centimeter. And that, in a sense, is also a unit used in the metric system, because the gram is a fraction of a kilogram and the centimeter is a fraction of a centimeter. So it's used, actually, as a matter of fact, it's more commonly used in astronomy, grams per centimeter cubed, than kilogram per meter cubed. In a sense, the question was asking about the metric system. So the correct answer really should be kilogram per meter cubed. So if people were using kilogram per liter, which is also another multiples of a volume, or a gram per cubic centimeter, you probably need to also get some partial credit. So some of those questions of this type, that's why I need to go through the entire quiz and regrade it. And that is when you see your grade. Now, here is item 1 of the discussion today. If you have an issue with the grade, whether for this quiz or any other, please, let's have a meeting together and let's discuss that in private, okay? So that I can go through it, analyze it, and then show you basically how it's supposed to be, okay? So that is the first item. So what I want to write in here is that basically, please communicate with me regarding your grade. Don't let it until it piles up and at the end you have questions about 2, 3, 4 assignments, okay? So that is what I want you to do right now, okay? So that we keep that out of the way. Now, the topics of the week, the content for this week, week 5, are going to focus mainly on the solar system. We're going to look at the entire solar system in the big picture and see what makes up the solar system. I mean, the biggest player is the sun, of course. The sun is the #1 item in the solar system. There is no question about it. Followed by 8 planets. The biggest player in those planets is actually Jupiter. Okay, followed by Saturn to a lot less extent. And then the scattered 6, the remaining 6, with 2 being big, namely Uranus and Neptune, but not as important as the first 2, as I mentioned. And then you have the 4 inner planets. And we will see the composition. The key word in here is the density. The 4 inner planets are more dense than the 4 outer planets, which tells you of what are made up of. If you know something, its density, you have an idea of what makes it. And that is the story with the planets in the solar system. the 4 inner planets, namely Mercury, Venus, Earth, and Mars, are more dense than the 4 outer planets. That means if you take a liter of each and every one of those planets and you compare them, you see a pattern. The first 4 weigh more than the last 4, namely Jupiter, Saturn, and Uranus and Neptune. They weigh less for the same volume as the inner ones. You ask yourself, why is that? Well, because the inner ones are made up of basically rocks and minerals, mainly, whereas the outer ones are made up of gas and maybe some sort of ice structures, that's all. Okay, icy gases and so on and so forth, ice and gas, that's really the 2 components. As a matter of fact, the densest planet in the solar system is Earth. It's more dense than anything else. If you take 1 volume of it, 1 liter of it, compared to all of the other planets, you will see it's the most dense planet in the solar system. Followed by Mercury, actually. Mercury is the 2nd most dense object, most dense planet in the solar system. That's one thing. The least dense of them all is Saturn, actually. Saturn is lighter than per liter than anybody else. As a matter of fact, Saturn is even lighter than water. If you take Saturn and you find an ocean big enough to contain it, there is no ocean big enough to contain it, by the way. If there is one, Saturn will float, it will not sink because of its low density. So this is basically the planets, which are the 2nd most important thing of the solar system. Then, of course, you have the moons. All the outer planets have moons. All the inner planets do not have moons. I mean, with the exception of Earth, which is kind of weird. It has a moon. So it's really an odd thing. Mars has a couple of moons, but those moons are not real moons in a sense that we talk about, and they seem to be captured rocks. Okay, so those are some of the properties that we talk about in terms of the solar system that we need to know of. So when it comes to moons, the Earth is an exception. So we need to explain this exception. What happened to it? How come the Earth has moon, whereas it really should not have a moon? Okay, whereas all of the outer planets have moons and have a lot of them. Okay, so that is a distinction, including the so-called dwarf planets, which brings me to the next type of object, which are the dwarf planets. Okay, dwarf planets like Pluto, for example, has 5 moons. Okay, so all of the other dwarf planets, Pluto is a dwarf planet, Eris is a dwarf planet, which is bigger than Pluto. Haumea is another planet, dwarf planet. What is it? Makemake. There is another one that is Quawar, which is a good word to use for your Scrabble games if you play Scrabble. And then, of course, you have Ceres, Sedna, all kinds of dwarf planets that are out there. Ceres happen to be inside the between Mars and Jupiter, but the rest of them, they are most of the times past Neptune. Okay. Then, after the moons and the dwarf planets, of course, come the asteroids, and we have a lot of them. We have actually a bunch of them. There is the group between Mars and Jupiter, and the so-called asteroid belt. And then you have the other asteroids that are sitting past Neptune, and those are in the Kuiper belt. Okay, so those are the 2 main asteroids where they sit. And then there is another region which is extremely far. And that region is where the remnants or the ejected materials from the solar system when it formed, and that is called the Oort cloud. So this is basically where now there is a distinction between the asteroids and the comets. Comets are actually most of the part exist in the Kuiper belt and beyond. Comets are icy objects. As a matter of fact, the objects in the Kuiper belt, they are mainly out of ice and basically carbon-based materials, whereas the asteroids in the asteroid belt, they're made out of rocks, just like basically the inner planets are. Now the comets have a distinction that they have this eccentric path, and as they are far away from the sun, they are frozen ice. When they get closer from the sun, they start to melt. And the ice starts to basically evaporate. And as it evaporates, it is being pushed from the sun and develops a tail. As they get closer from the sun, you will see the tail. And then as they pass by the sun, it's always the tail is facing away from the sun because of the radiation from the sun. And as they pass the sun, they come back again in the opposite direction. At some point, they pass there is a line in the solar system where things start to freeze, where water becomes ice. So at that point, they regain their icy structure and they become a rock solid basically, and they continue in their path around the sun in this way until they come back again. So those are the objects in the solar system that we talk about most of the times. And this is what I'm going to introduce today. And this is what I'm going to show you actually from Universe Sandbox. That's why I have my laptop actually sitting in here. So I need to grab it, okay? Because it has some of these features in here. So let me first of all close this thing out of the way. Before I do that, let me share with you the screen, because there is another point that we need to talk about today. And that is the history also of the solar system. How come the solar system came to be, which is a very important point, okay? Because it explains a lot of things. So, and then how do we know what we know, okay? And the other item of the discussion is going to be about the theory. Because we're going to develop a theory, but I really want you guys to understand what the word theory in science means, in astronomy especially, okay? So let me share the screen so that we see what we have this week, okay? Obviously, the objectives. I'm going to get at some point to the homework assignment, and I'm going to go in detail about each and every one of those problems. So I hope to answer all of the questions. And if there is any lingering ones, I'm going to answer them later on if you want to. The point I'm trying to make in here about homework assignments, unlike quizzes and tests, they are not to test knowledge. They are actually to help you understand concepts. So I want you really to do them and be confident in your answer. If you have any question about it or not sure about it, that is when you let me know or have somebody to work with to resolve that. So let me first of all talk about the objectives of this week. I guess you guys are familiar with the construct by now. You know exactly basically what to expect. The discussion item is going to be here today, okay? So let me go through this one in here. I already talked briefly about these items in here. This is basically what makes up the solar system. By far is the sun, okay? And then you have the inner planets in the order from their proximity to the sun: Mercury, Venus, Earth, and Mars. In terms of size, Earth is the biggest of them all, followed closely by Venus, and then Mars, and followed after that by Mercury in terms of size. In terms of the outer planets, Jupiter is the biggest. Jupiter is actually the biggest planet in the whole solar system, and all of them are bigger than Earth. So this outer planets, both in mass and in physical size, both in mass and also in volume. Then Saturn, Uranus, and Neptune, again, in the order from their proximity from the sun. Dwarf planets, they are not actually in particular order, otherwise Ceres should be the first, because it's closer. It's actually between Jupiter and Mars. Then you have all of this. Some, you still have more, okay? This is not the entire story of the dwarf planets, okay? One particular one of them is actually Haumea has this weird shape that it is kind of, because it spins so fast on its axis, it's not a spherical anymore, because it's not a sphere anymore. It has actually this elongated shape, but they have all kinds of interesting properties, okay, all of them. We'll talk about the moons. As I was talking about earlier, the moons, all of these outer planets have moons, and actually they have another thing I didn't mention, and that is rings. All of them have rings. The obvious one, or the most famous one, is that of Saturn, but all of them, they do, okay? And the moons, they do have moons, except in here, Mars has a couple of moons, Phobos and Deimos, but those are actually not real moons. They're captured rocks from the asteroid belt, most likely. And one of them is actually headed toward Mars at some point in the future, is going to basically collide with it, and the other one is losing distance. Basically, it's escaping from its pull. So at the end, it's going to end up basically of what it was. So it was an event that happened sometime probably in the past, but now it's going to lose them. Venus and Mercury do not have moons. The Earth has a moon, and that is an odd thing that we probably need to explain. I mean, the leading theory right now, and I'm going to talk about the word theory, is that at some point in its past, Earth collided with a Mars-sized object. So there was another planet that's probably formed immediately in the vicinity of the Earth, maybe on the same orbit, okay? And it collided from the Earth at a given angle, which is about, that explains actually the tilt of the axis of the Earth. And the debris from that, basically, some of it gets stuck in the Earth, and others were actually ejected. And the materials that were ejected went for like a ring formation, and the end they start to coalesce again and to form the moon. There are at least a lot of evidence for it. Two of them or three of them I can mention. One of them is the tilt of the axis of the Earth. The other one is the common materials for both the Earth and the moon that seem to be that they must have shared some sort of a past history where they were connected. And then there is actually another explanation for that one, and that is the inner core of the planet Earth has an irregularity in its shape. That's probably the remnants from the material that went inside the core of the Earth and basically produced that irregularity. And you can see that actually from the properties of the magnetic field, and actually the properties actually not of the magnetic field, more so the seismic waves due to earthquakes. You can actually see that the shape is a little bit odd. So there is evidence for that to explain the fact that the Earth has a moon. Okay. So these are the other structures. Then the asteroids, I mentioned the two types, the Kuiper belt on the outside, and then the inside, which are the asteroid belt, and the comets. The shapes you will see clearly from the animation in here that these shapes are actually following the path, following Kepler's laws beautifully, and explains the periods, explains the distance, and explains everything about the solar system. One of the things that we need to explain, and that is not clear in Kepler's laws, is how come all of the planets are for the most part sitting on the same plane? Okay. The fact that they sweep same angles, sweep equal areas at equal times, that can be explained by Kepler's laws because that's based on his observation, and Mr. Newton was able to explain. And that has to do with the conservation of the angular momentum in terms of a quantity. It turns out the angular momentum is a vector, and it's conservation also, because once the material starts to coalesce, so here is what happened, at least the leading theory. Here is a caution about the word theory. When somebody tells you I have a theory, they most of the times, or at least in the culture, they mean I have an opinion. When they tell you my theory is, somebody else tells you my theory is, they mean in everyday speech that they have an opinion. This is not so in science. A theory in science is far more than an opinion. Let me explain how far you can get into a theory. You do observations. So that is a big distinction. Measurements. And in this case, you do a lot of observations. You do spectral analysis. You analyze the spectrum to see exactly what kind of frequencies you have. You do observation, for example, the motion in the sky. And you see how much angle is swept at different times. So you take the position today, the position tomorrow, the position the day after. So these are observations, these are actually measurements that you're doing, okay? And you analyze the data and you come up with a guess, which is really an educated guess, not a random guess. It's based on information, based on prior knowledge, okay? And based on your data. So it's really not a wild guess. It's really an educated guess. And then you test that guess and you come up with a model. And your model now explains, if it's successful, of course, explains what you have seen and goes a step beyond, predicts something that you didn't see. And sure enough, you go and measure it and it fits the model. So the collection of this work from the experimentation from the before, the model, the theory, the model, the hypothesis, the testing, and then the predictions and the measurements, this whole thing, this whole body of knowledge is what we call theory. It is not an opinion. It is a solid foundation. This whole thing has now roots in a lot of evidence. So it's not something that we use loosely. The point I'm trying to say in here is, and this is the second item of the discussion, is a theory is not an opinion in science. Does this make sense to you guys?
Yes, very, very clear.
Thank you. So this is the item 2. A theory is not an opinion in science. Maybe in somewhere else, maybe, but not in science. It goes beyond. So what is the theory now as far as how the solar system is concerned, how it came to be? Based on observation of some sort of other also, I mean, you take, for example, your telescope and you gear it toward the nebula and you see that there is actually steps, different steps, as you can see, of the process that I'm going to describe. So at some point in the past, there must have been a supernova in the region where the Earth is. Why do we know that there is a supernova and not just some sort of an intergalactic gas that assembled, mainly hydrogen and helium, from the remnants of the how the universe formed before? Well, because of the heavy elements that exist on Earth and everywhere else in the solar system. Iron is a good example for it, and iron cannot be formed except through a supernova process. So there must have been a supernova in the region where we are right now from stars that existed before the sun. And those materials, after a long, long time, they started, due to gravity, started to come closer to from one another. They attracted one another, and the tiny specks, basically, of dust started to grow. And as they grow, the force of gravity becomes stronger and stronger. So they attract more and more. Here is the problem. Let's say, for example, I have two pieces of rock, this one and this one. This one now gets closer. As it gets closer, it needs to speed up. Why it speeds up? Because the potential energy decreases, it goes smaller and smaller. The potential is inversely proportional to the distance. So it's in magnitude, it increases, but it's a negative number. So when the magnitude of a negative number increases, it went down. So the potential energy decreases. That means the kinetic energy must increase. So as they get closer and closer, they spin faster and faster, and that's fast and fast motion increases the temperature. The phenomenon is similar to the rubber ducky. If you have one in the bathtub, just open the bathtub and let the rubber ducky at far away from the sink, it's going to spin slow. As it gets closer from the sink, it's going to move faster and faster until it goes in. Okay, so that's similar in the sense that as the particle get closer and closer, they speed up, and in turn, as they get higher and higher kinetic energy, their temperature increases. So now imagine with me, at some point, this disk of material is getting closer and closer and spinning. And because there is no external forces to cause it to spin, all of it is internal, exchange between potential and kinetic energy, then the external torques are zero. The angular momentum, according to Newton's laws, must be conserved quantity. The disk flattens, just like the dough for the pizza, it flattens, and hence all of the planets exist in the same plate, in the same plane, okay? And the conservation of angular momentum makes these quantities basically move faster and faster, closer, and further move slower. So imagine with me the following scenario. In the center of this all, a lot of materials are gathering together. Their temperature is increasing because of the higher movement, the higher kinetic energy. The density is also increasing because of all of these materials coming together. So more and more material coming together. At some point, and this process did not happen just in the center of the whole, basically a cloud, if you wish. It happened also in the other edges of it. Immediately after this one, there was another bulge also that starts to develop somewhere where Jupiter is. So Jupiter starts to gather a lot of materials, mainly hydrogen and helium, just like the sun, hydrogen and helium in the center. And other planets also started to do the same thing, collect more and more stuff. And they continue to grow. The point being in here, right in the middle of it, where the sun is forming, it was still a protostar at that time, not really a star. Too hot, extremely hot, but not nuclear yet. Extremely dense, hence the density, the pressure was extremely high. Because of the high pressure and the high temperature, the hydrogen started to fuse in a nuclear reaction. And immediately inside the core, when it went nuclear, because of the high pressures and the high temperatures, radiation came in all directions and expelled all the materials, the light dust that was feeding all of these planets, expelled it far away to what is basically right now the Oort cloud, okay? At that point, only the big rocks remained, mainly the planets and the moons and all of the big asteroids and things like that. The smaller ones were ejected. So in a sense, when the sun went nuclear, it starved the remaining planets for growing and becoming as its size. In a sense, Jupiter was close from actually achieving the same goal. Jupiter was big enough, if it grew any bigger, it probably could have developed nuclear reaction and its core also became another star. But because it was starved also from more hydrogen and helium, then it could not continue. Now it's just a planet. So that's basically how the solar system formed. How do we know that? Well, one of the ways, first of all, in terms of the age, is radiometry, basically trying to determine the age using radioactivity. For example, we know at least for potassium 40, isotope 40, it can go into calcium 40 by emitting an electron. This is called the beta decay. Okay? This is about 90% of the times. 11% of the times, the same potassium 40 can capture an electron actually and change into an argon. Argon is actually a noble gas. It doesn't interact with anything. And again, that is 11% of the time. So if I have a sample and I can determine how much argon and calcium is, and if I know the half-life of this process and the half-life of this one, I can determine the age of that rock. And that is exactly what we use to determine the age of the solar system. As a matter of fact, to be about 4.5 billion years. In addition to other phenomena that I'm going to describe, and that is, for example, the early bombardment that the solar system went through, because there was a lot of remnants, big rocks that remained from the formation of the solar system, and those rocks must go somewhere for the most part because the solar system was still going through an agitation and rearrangement, and it is still an ongoing process still today. Some of the planets move in, some of the planets move out, and in doing so, they moved those rocks, and there was a heavy bombardment period where a lot of these rocks were basically hammered all of the other planets. We can still clearly see it at night. If we look at the moon, we see a lot of craters on the moon. And we don't see it as much on Earth, other than if you have to go to, for example, Arizona, because of the fact that Earth has weathering on it. The weather, especially the plate tectonics and the geology on its surface, it enables it to renew its surface on a regular basis. That's why most of the times we don't see this on Earth as much as we see them, for example, on the moon. So again, this is how the process is. So let me share with you what I promised to share with you. Let me first of all get it going on this computer. I have a software in here. If you have it, it's a very nice software. It's on my laptop because on my computer it would require a lot of computing power and then slows down the whole computer. That's why I put it separately on the laptop. And it's called Universe Sandbox. If you happen to have a good enough video card, it's actually very good software to have because it simulates a lot of things. It simulates planets, simulates stars, it simulates the collision of stars and galaxies, and do a lot of things, a lot of physics actually. It's based on a real, it's sometimes kind of slow to start. Did I start it or not? What I did. Yes, it did start. So let me share it the minute it pops up. Okay. It requires a lot of computing power, and the computer actually becomes too hot. That's why I really don't like to run it on the desktop, because if I do it, so let me stop the time first of all on it. And ever find it in here. Okay, and let me share it. Share. Yes, let me stop sharing this screen first, saying that you're sharing the other screen. Yes. Okay. So this is a view of the solar system from a distance of about probably 5 astronomical units. As a matter of fact, if I can hover in here, it should tell me how far. Let me get this thing out of the way in here if I can. Look at the sun. It should tell me how far I am from the sun. Distance to you, it's about 5.06 astronomical units, just around the edge of Jupiter. Okay, this is from Jupiter, or at least above Jupiter probably, because we can see Jupiter in here. I can see also Saturn and the horizon and all of that. So let me click on the sun again, and let me zoom in on it. This is by far the most important object in the solar system. So I'm trying to go in, but not too close, because it's really still a bright object, okay? Oops, I went too far. Anyway, the sun, for the most part, basically it has this outer layer, which is the visible layer, okay? But inside of it, it's made of its core, and the core is mainly hydrogen at this point, and hydrogen is fusing. You have 4 hydrogen nuclei, meaning it's really 4 protons, okay? 4 protons, they combine to make 1 helium nucleus. The helium nucleus is called an alpha particle. Why? Because it's too hot for the hydrogen to have captured an electron to become an atom. And the same thing for the alpha particle, it's too hot, the temperatures are, for it to capture 2 electrons to become a neutral helium. So that is what's happening in the core. Imagine with me right now that one nuclear reaction, which is a very, very rare event, by the way. That's why the sun lasted so long. Captures 2 4 protons. Somehow they combine and they make a helium atom. The temperature is so high, the density is so high, that photon, the light basically from that nuclear reaction, well, first of all, it's a very high energy. It's going to immediately collide with another particle in there, which is mainly all of the particles that are in there because of the high density. And that collision followed by another collision, followed by another collision, followed by another collision. And then at some point, it's going to escape the core of the sun. After it escapes the core of the sun, it's going to go through a big layer, and that layer is the convection layer. That layer, can I have a cut from the sun? Composition? No, it does not show me the composition, because it's mainly 0 iron, 0 silicate, 0 water, 0 hydrogen is 100% hydrogen. Basically, it's staying for the most part. It's actually, it's gas, okay? That's what the composition of this, the sun is, okay? It's actually 75% hydrogen and 25% helium, for the most part, okay? Again, you ask me how we do that? Spectral analysis, it's easy, okay? Analyze the spectrum and break it down into components. Okay, so imagine with me that that electron left the core and now it's in the convection layer, where the gas is actually going like inside the oven, not the oven, inside the the convection oven, or inside the soup as you're boiling, for example, and it goes boiling. So in this case, the heat is taken from the core to the upper layer, and the photon actually has to travel through that distance in order to reach the upper layer. Once it reaches the upper layer, it's going to escape and come all the way to our eyes. This is the light we see. Do you have any idea how long it takes for a photon from the time basically it is formed from the nuclear reaction to the point it reaches us? Roughly. Remember,
No idea. No idea.
light travels 300,000 kilometers per second. There is 150 million kilometers. So if you do 150 million kilometers divided by 300,000 kilometers, the number should be about 8 minutes. But it takes more than that. It takes about 100,000 years. Why? Because those collisions inside the core. So the light that forms today will not be seen until 100,000 years from today. When we see light today, that is when the first humans basically started to walk in Africa. So it's 100,000 years ago. So it's a long, long time ago. So, or the human light people, not the probably modern humans, they formed a little after that. I mean, about 60,000 years ago or something, according to current studies. Anyway, the point I'm trying to say in here is that that light comes in. So how in the world do we know what we know, what's going on in the sun? Let's say, for example, today, the core collapsed on itself, destroyed, or some imbalance, something happened in the nuclear reactions that they slowed down or they sped up. So how can we tell that the sun is going to explode or implode or something happened to it? Of course, we cannot tell it from the light because we have to wait 100,000 years to know that. So what is actually coming out of that, and I showed you the picture earlier from when I shared the screen, those two tiny nu symbols, the Greek letters nu, those are called neutrinos. Neutrinos, they come unimpeded from the core of the sun all the way to the Earth, and they take about 8 minutes. So we will know what happened to the Earth, to the sun, not because of their light, but because of those messengers, because they're called neutrinos because they don't have a charge, they don't interact with anything, and they're extremely hard to detect. But we have several detectors on Earth to find them, and those are the ones that tell us what happened to the sun, if we should pack and leave or do something about it. Okay, we have about 8 minutes basically to do something about it. The point being in here, this is how we know what happens in the sun. The sun, as I was saying, is the main player in the solar system by far. It's both in mass and in size. It's about 700,000 kilometers in radius, which is about 1.4 million kilometers in diameter. It's a huge structure. Okay, and then now the planets. Okay, let's find them. Look at the paths in here while you're looking at this. So this is Mercury. I was talking about the cratering. Let me remove this and go back to the overview. If I go into let's keep the structure. It's an interesting thing. See here, the composition. You can go through these numbers in here. It has iron, it has silicate, which is really a rock. Okay, we don't know if it has any water whatsoever. Where is the density? The density is a key word to look at in here, and it's in grams per cubic centimeter, and it's 5.43, which is the second most dense planet in the solar system after the Earth, which is 5.5. Okay, so again, that tells me about its composition. So let's look at it up close in here. See if I can see. This planet has a large core compared to its size. Okay. Come in. Oh, it's too close. I came in from the dark side. We came and left the sun in front of us. So let's look at it and rotate it and spin it and see. It doesn't look too different from the moon, does it? As a matter of fact, this is also an evidence of the early bombardment. Okay, so this is Mercury. And this is, there is different views in here. I don't know if I can change the view to, I don't want to deal with it right now, okay? To the surface and how it looks like. So let me close this for right now. Okay, so this is Mercury. Mercury is a very close planet from the, this is the closest planet from the sun. As a matter of fact, there are some theories that talk about the fact that probably it was a giant just as big as Jupiter is right now, but at some point, because of its proximity from the sun or it migrated toward the sun, it lost all of its atmosphere. And this is the core of that planet that's left, basically. But I don't know about that theory, so we'll probably have to read more about it to see if it's more articles about it to support it, basically. Anyway, the next one, as you can clearly see from the background in here, is Venus. And Venus, you can clearly see the core is a lot smaller, relatively speaking, of course, to the planet. And it really has a, let me see if I can zoom onto it. Okay. You can't see much from Venus if you zoom onto it because of its atmosphere. It has a very, very thick atmosphere. As a matter of fact, the pressure on its surface is about 100 times. It's about 90 times, to be more specific, than that of the Earth because of its extreme thick atmosphere. It's mainly carbon dioxide, though, and sulfuric acid and all kinds of chemicals in there. No water, though. It must have had water in the past, and there are some recent studies that confirm that. But what happened to the water? Most likely because of the heat that was generated on its surface. That water was broken down into chemical components, namely oxygen and hydrogen. The oxygen recombined with the carbon and the other elements to form CO2. And the hydrogen, because of the extreme heat, gained a lot of heat, a lot of energy, a lot of basically kinetic energy. And it, because of its low mass, also it went up to the upper atmosphere, and because it still has a lot of kinetic energy, a lot of velocity, then it escaped the entire planet. So now the problem is all of the water basically is gone because of that. You cannot recombine it somehow in a process and recover the water. So this is an example of a terrible situation that happened into some planets in the solar system. It is really the sister planet to Earth. It's very slightly less than the Earth, close to it in size, proximity, and all kinds of things. This is the closest planet to the Earth. Then, of course, the Earth. A lot of the things that we know about the solar system, we know them actually from studying the Earth. And then, especially in terms of geology, right now we still have the Earth has this atmosphere in it, which is really mainly nitrogen for the most part, with a little bit of oxygen in it. The oxygen is really produced by the plants on it. So it's really a life, it's produced by the plants, which is really taking all of the other elements, namely carbon dioxide, and breaking it into oxygen and retaining the carbon for other processes, making basically organic materials out of it. So it's really, life has influenced the shape of the Earth. Okay, that's the point in here. So this is the planet Earth. Then, of course, comes Mars. If I can find Mars. It's probably on the other side. Come on. Here is Mars. Mars is teaching us a lot about also the solar system. Okay. Oh, because of this in the way, sorry. Okay. They changed the view in here. Why is it doing that? Okay, good. Okay. So again, we're going to spin to the front side and look at it, put the sun behind us basically, and look at Mars. Mars has some nice features in it. Let me zoom in. One of the features that it has is this huge canyon, which is really around the equator, but it's at night right now. And if I let the time spin a little, so it's going to spin, spinning too fast now. Can I change the clock? Is it how many days per second? Yeah, okay. So basically, another feature that is actually is Olympus Mount, which is a huge mountain on the surface of Mars. Olympus Mount is actually taller than Mount Everest in here on Earth, yet it's wider extremely wide. As a matter of fact, it's the size of France, meaning that if you're going to climb the mountain, you really are not going to notice, say, that you are climbing a mountain. It seems like you're walking on a flat surface because of its extreme sheer size. And the problem here is the canyon I was talking about in here. That is actually much bigger than the Grand Canyon, than any canyon on Earth. It's actually the size of several, basically almost the size of the United States. The point being in here is that we've been doing exploration of objects in the solar system using rovers for the most part, basically machines that walk on the surface or drive on the surface of the planet or the moon, or basically for the most part the Mars and the moon. That's what we did successfully. But now we've used a drone. Ingenuity was launched in February with Perseverance, and Ingenuity was able to fly on the surface, which was really a big achievement on its own. Okay, and it did a lot of missions, to the point that NASA now is thinking that the next mission to Mars is going to be a flown mission. As a matter of fact, they're going to actually build a rover much bigger than a drone much bigger than Ingenuity, and probably is going to allow for exploration much better, because you can see a bigger area and you can see the features, the geology in a much more detail, and probably would be able to explore more and more areas on the planet. The Chinese are actually planning a fixed wing plane also, or at least they're thinking about it on Mars. And NASA is actually doing the same thing now for Titan, the moon of Saturn. So there is a lot of things that you can build. So we are entering a new era, basically, of space exploration that uses probably still rovers, but we probably are going to also explore the possibility of having drones on other planets. So that's interesting. Of course, we cannot do it on the moon because the moon does not have a surface, at least if we're going to have a takeoff in a sense that we do it on Earth, because you need still air for the blades to work. Okay. So, but on Mars, albeit the problem was the density of the air is there extremely low, and we were worried: can we gain enough lift so that we can lift that thing? And of course, it was a challenge because we have never experienced Mars basically flight, and this is the first time we did it. So it's really a major achievement, and we're learning as we go. So this is still fresh from the oven. These are studies that are basically the Perseverance landed in Mars. So this is what we know, at least based on what we explored Mars so far. Okay, after Mars, of course, comes Jupiter. But before I go to Jupiter, let me see if I can find Ceres, because Ceres is between Jupiter and Mars. And I'm going to briefly talk about that. And it should be somewhere in, here it is, okay? This is actually a dwarf planet, and it exists in the asteroid belt with a lot of asteroids in there. Of course, Jupiter comes in, and Jupiter is interesting in its own features. It's made of a lot of basically gas in the upper atmosphere, and the gas is hurling very fast, especially depending on the planet, because it's going so fast also on its axis. And that generates a lot of basically motion on its surface, and it has all of these features on its surface, among other things, the big eye on Jupiter. And it has moons, and it's really an interesting system on its own. As a matter of fact, the moons revolving around it look like exactly another solar system, because you have some 70 odd moons going around its axis. And this is true actually also for Saturn. Let me close this. This is also true for Saturn, which is the next big object. Now we are in the planets that are in the outer solar system. The minute we exit Saturn, we're going to find the planet Uranus and then Neptune. I'm going to look at Neptune. Both of them have this bluish color in them because of their methane structure. Okay, actually, this one is a little bit greenish in it, or than Neptune. Okay. Neptune is colder, actually, and Neptune is the last planet that we know of. Anything outside of Neptune or past Neptune is called the TNO, Trans-Neptunian Object. Okay, that's what the TNO stands for. Pluto is one of them. That's a dwarf planet. Koar is another one. That's also another dwarf planet. Makemake is another one. Here it is. okay, which is another dwarf. Haumea is the one I was talking about, its shape being a little bit odd. I don't know if you're looking at the shapes in here or not, but that's where they are. And those are some, where is Eris, which is the biggest object in there? Okay, Eris should be somewhere in here. It's a little bit further. Here is Eris. Okay, and there is Sedna. Sedna has a very, if I'm going to find its path, I need to zoom further. You see how its path is? It's a very, very eccentric path. As a matter of fact, I need to even move zoom further. At some point, we are lucky enough in time that it is probably close enough from the sun. Down the road, it's going to be extremely far away from the sun. As a matter of fact, to a point, how far are we from the sun right now? Where is the sun? I'm still zoomed in on Pluto, not the sun. I mean, just to give you an idea of how far we are from Pluto itself, we are 1,000 astronomical units from Pluto, which is about 30 astronomical units from, or 40 astronomical units from the sun. So this is where Sedna is, okay? Right now, it's about 965 astronomical units, and it's still, okay? Okay. So the point being in here, this is the solar system in a nutshell, and at this point, we are in the Kuiper belt. Still further away than this, there is the Oort cloud. So this is an overview of the solar system and its structure, and you see the orbits, and you see Kepler's laws in their beauty, the paths, and everything else in there, and the fact that they're all on the same plane to tell you that there is a physics behind it, and the physics that the conservation of the angular momentum. So all of these concepts in here are explained beautifully with this simulation. This is a simulation. This is not like the stellarium, where the stellarium is actually an actual view of the region where you are. This is basically a simulation from wherever you are. You can simulate things. As a matter of fact, I did a movie a few years, last year, I guess, or so, using this software where I had a bunch of planets basically colliding, and you can do all kinds of physics if you want to, basically playing around with black holes and colliding them with neutron stars and see what's going to happen, and produce supernovae at will, and doing what if scenarios. What if the sun has twice the mass or less the mass, or what happened to the orbits? It's really interesting things that you can do with this one. So if you have time, it's not expensive really software. It's about $20. It's a good software to have. So let me stop sharing the screen and let me go back to the first computer. Let me exit this program because it's really and let me talk about the second item I was planning to talk about today, and that is the homework. Kind of, Christian. Yeah, but they don't spiral in. They spiral in. Probably that describes more Phobos than anything else. That's a spiraling into planet. Okay, it's going to hit with, because when we say spiraling, it's like going in, and at some point it's going to collide. But for the most part, they're on stable orbits, and those orbits, they are actually elliptical orbits. Okay, make sense? Okay, so let me share with you the screen again where we were earlier. This, I'm hoping that you guys read through these two units, 35 and 34. Okay. And if you have any questions, please let me know. We should be able to resolve those things. Okay. So let me go back into where we were. Can I do this? Can I go back like this? Yes, I can. So again, the week before review, the discussion items are going to be here. The first one is, please, if you have any questions about your grades, ask me. We'll have to do them in private sessions. And the second one has to do with the theory, the fact that the theory is not an opinion. Okay. In science, the theory is not an opinion. It's far more, it's a body of knowledge, really, to be more specific. Okay. So let me talk about this assignment. Oh man, we still have very little time to do it, but hopefully we can do it. Okay. So let me pull the screen in here, and let me go to your class. And let me change pen colors. I'm not sharing this right now, but I'm going to share it soon. So let me read the assignment again for with you guys so that we're clear. So we have 5 problems to do. Okay, the homework. Not today, they're not due today, they're not due this Saturday, but next Saturday. So you have roughly about 10 days or more, actually more than 10 days to complete them. I'm going to go through each and every one of them and hopefully we'll clarify. And if you still have any questions, I'll be more than happy to discuss them on a one-to-one basis with you. Hopefully you have a team by now or contact some people. I know a lot of people did not reply to my survey. So once we have that, you can work with people. Otherwise, it should not be hard to do. Okay. Remember, homework is not an exam. Homework, you're supposed to do it, enjoy it, submit it, and learn from it. Okay. That's really what I hope to achieve from it. So let me stop sharing the screen and share with you another screen if I can find it. Here is a screen. I'm going to move it to the other. No, it's going to stay in here because it's not going to work because the mouse doesn't. So let me move this one to the other screen. And now let me go back and share that screen share. So what happened in here, if you don't have the book, the questions are actually on Canvas. Okay, so I wrote them for you guys. It should not be hard now to do them. So all of the problems are in there. So we have problem 10, 11, 12, 13, 14. And they are all from the same page, 99, whichever edition you're using, 5th edition or 6th edition, it's the same page, the same problems. And if you don't have the book handy with you, the problems are written in Canvas, so you should not really go too far for them. So the first problem 10, it tells you a series. Remember when I showed you series, it was between Mars and Jupiter. So we should find it between Mars and Jupiter. That's really what the problem is. So it tells you series has a period of 4.60 years. That means 1 year on Ceres is about 4.6 years on Earth. Okay, a little over 4.5 years. Okay, what is its semi-major axis? So the first question should be easy. Okay, so we know p squared is equal to a cubed. That is the third law of Kepler. They gave us p. So we should be able to square that number. So all I have to do is multiply p times p. So it's going to be 4.6 times 4.6 equals to a cubed. And 4.6 times 4.6, if I plug it into a calculator, and I did it earlier, and hopefully you guys will do it, is 21.16. This must be equal to a cubed. Of course, I have to really be careful with this kind of math because the calculator sometimes gives you more precision than what you have. I have this number is important, this number is important, and this number is important. Any zero after the decimal point is important. So what we're saying in here is that I know the answer with a 3 important number, and they call it 3 significant figures, and they write it 3 sig figs. Okay, 3 significant figures. So the answer should only be 3 significant figures. You cannot make up more precise answer in calculating than what you did in measurement. Since the measurement was only able to give you 3 significant figures, the calculator should not give you more than 3 significant figures. The calculator doesn't know, should give you all the numbers that you want, and you have to make up your mind with it. So I have 1, 2, and 3. I have to ask this question, is this number 5 or more? And the answer, yes, it is 5 or more. As a matter of fact, it's a 6. Since it's a 6, I have to add 1 to this number. Of course, I'm not going to write this number. I have to add 1 to it, and the 1 plus 1 is 2. I don't have to carry any number in here, so this number does not change, and this does not change. So the correct answer basically is for a cubed is equal to 21.2. I need to find a from this. 2 ways of doing it, either using a calculator, let me share with you how I do it on this calculator. Maybe you have a better calculator, but it's a good idea to have access to a calculator. So a cubed, first of all, so let me share the screen with you first. Share. On this calculator, I'm going to write 21.2, that is a number, to the power. The cube is to the power 1/3, by the way. This is from your algebra class. And to the power 1/3 should give me 2.7676550072889. Again, this is what the calculator is trying to give me. This is A, by the way. A is the cubic root of this whole thing. But I have to be careful with this number because I only am going to retain 3 digits because of the same issue, same point I was talking about earlier. So, what happened in here? Why everything is erased? So A then is the cubic root of 21.2, and that number, according to the calculator, is 2.767 and some other stuff, some other change. The reason why I'm not writing those other change because they don't matter. I have only 3 significant figures, so I cannot make up more significant figure than what I started with. The 2 is good, the 7 is good, the 6 is good, but is it really a 6 or not? We will find out. I ask, is this 7 5 or more? And the answer is yes, it's actually 7. It's more than 5. Since it's more than 5, I'm not going to write it. I'm going to add 1 in here. And the answer is going to be 277. And the reason why I left this 7 is because I didn't have to carry any number with me. So when I add 1 to 6, it's becomes 7. And that is the answer. So A, the semi-major axis is 2.77. Let's see what's going on in here. If I take the sun here, here is the sun, and get all the way to where Mars is. Mars is at 1.52 astronomical units from the Earth. This is the units, astronomical units, by the way, from the sun. The Earth is somewhere in here, 1. So that's where the Earth is. Exactly 1. Venus and Mercury are in here. Then Jupiter is at 5.20 astronomical units. This object is more than 2 and less than 5. So it's somewhere in here. This is where Ceres is. It's actually 2.77 astronomical units. So just between Mars and Jupiter, as we saw it in the simulation earlier. So that is basically what the numbers are. You see the value of doing homework? You learn more with numbers. And all of the things I described earlier, they're actually based on numbers. Numbers tell far greater the story more accurately than anything else. Okay, that's why it's important. Now you calculate A and you find just where it needs to be. More than 1.52, which means it's further than Mars, and less than 5.20, which means it's closer than Jupiter. That's where you put it. So that's the questions 1 and 2. Actually, we answered where it is and we answered how far it is and everything else. So that's question 10. Let me find where question 11 is. Question 11 has to do with Sedna. Remember when I mentioned Sedna, the dwarf planet Sedna, I said it's very far, okay? Well, they tell you in 11 that it has its period, its A is 526 astronomical units. I mean, just to give you an idea, just to give you an idea, Jupiter is what? Not Jupiter. Jupiter is 5 astronomical units. It's a 10th of this number. Okay. The further Pluto is 40 astronomical units. This one is still more than 10 times further away. Okay. So this is A. We need to find P, basically. That's what the question is. And we need to compare it in the question to that of Pluto. Pluto takes about 248 years to go once around the sun, which is an amazing thing. That means the last time Pluto was in its position where it is today was 248 years ago, when the Civil War was still going on in the United States. Okay. So that is 1780 or 1790 or something like that. I don't know much about history, honestly. But that's really when this thing was in its position right now. 2.5 centuries ago. So we need to compare that of this one. So first of all, we need to find P for Sedna. So this is A for Sedna. We need to find its P. Well, P squared is equal to A cubed. And A cubed is 526 times 526 times 526. You're going to find a very large number. And if you do the math, you're going to take the square root, the normal square root, not the cubic root, the normal square root of 526 times 526 times 526. Okay, it's going to be something, I'm not sure. Okay, you need to check on your own with your own calculator, more than 12,000 years. Wow, that means the last time Sedna was in its position where it is today was 12,000 years ago. That's way before Moses and before the pharaohs and before everything else. I don't know, even if probably before even the Babylonians and all of these things. So it was a long, long time ago. So that's how far. And it's 1 year. That's 1 year on Sedna. 12,000 years on Earth. Okay. That's interesting. I don't know. You need to check this one. Okay. I'm just putting a number in there based on my estimates. Okay. So you need to do this on your calculator and check it. Okay. So of course, it's much, much bigger than that of Pluto. This is for Pluto, by the way. 248 years. That's because, sure, because it's further away. Now, question 12, problem 12. Already on my time, still good. Suppose an asteroid is discovered, by the way, well, the exam is coming soon, okay? So we really have to get into the mode of the exam one, okay? I think according to schedules, we have to finish it after we do the next unit, which is after next week. We really have to have our exam. Okay, suppose an asteroid is discovered with an orbit that brings, after week 6, we're gonna have the exam. So it's gonna be week 7, probably, when we have our first exam. Suppose an asteroid, so I'm looking at question 12. Suppose an asteroid is discovered with an orbit that brings it 0.5 astronomical units from the sun and as far as 5.5 astronomical. What is its semi-major orbit? What is its period? So here is a little bit of work that we have to do in here. They didn't give us everything straight out. So we have the sun in here. The asteroid comes within 0.5 astronomical unit from the sun. And then 5.5 times away from it. So this is the closest approach, and this is the furthest point. So this is the perihelion, this is the aphelion. So this is how the orbit of this asteroid is. This distance from the aphelion to the perihelion is 2a. And 2a is clearly equal to 5.5 plus half. So that's 6 astronomical units. From here, I can find a, which is 6 over 2, which is 3 astronomical units. Now, this is a, which is just this distance from either point. It's the same one. So it's 3 astronomical units this way and 3 astronomical units that way. Okay. Obviously, at this point, closer. I mean, it's almost as close to the sun as Mercury is, and here it's slightly further than what Jupiter is. So we found what A is. Now, all we have to do is find P now. Doing the same thing as we did before. P squared is equal to the square root of the cubic root. I'm sorry, let's cube things first. I'm sorry. So it's going to be 3 times 3 times 3. Okay. Am I doing it right? Yeah. Because each and every one of them is 3, and 3 times 3 times 3 is 27. Okay. So P itself is going to be the square root of those things. P is going to be the square root of 27, which you need to do on your calculator. So you need to calculate. And square root of 27 is slightly more than 5 years. Because 20 is 25, square root of 25 is 5. Square root of 36 is 6. So it's going to be slightly more than 5, slightly, a lot less than 6 years. So that is up to this point 12. Let's do 13 quickly. For 13, you have the sun, a comet reaches 1 astronomical unit from the sun. So at some point, the comet is as far from the sun as the Earth is. That's what 1 astronomical unit is. So this is where the comet is. The Earth is on this orbit, so probably the Earth is somewhere in here. It doesn't matter, but it's very close from the sun, as far as almost 1 astronomical unit. Okay, where the Earth is. At some other point, it's going to be very far. So it has this is what Comets is. So it must have developed a tail because the Earth is too warm for water to stay icy. So it's going to have a liquid that develops and does a tail and everything else that we have in it. Okay, at this point, and its closest approach and its orbit is 7 years. So we don't know how far it is in its furthest approach. It's an X. And they tell us it takes 27 years to go around the sun. So this is A, by the way. This is A. Okay, so this is the whole thing is twice A. So I know the period they tell us is 27. Okay. And I know P squared is equal to A cubed. Once I find A, I'm in business. I can find how far it is when it's far away. Because the question is, what is the maximum distance? And the maximum distance is this distance from the sun. From here to here, it's X. I don't know what that is. So I need to find it, okay? So, well, I know P squared, so I need to find A is equal to A cubed. And P squared is 27 times 27. And then A is equal to the cubic root of 27 times 27, and this should be actually 9. It's easy to check why it's 9. Because 27 is 3 times 3 times 3 times another 27, which is 3 times 3 times 3. And the cubic root will give you 3 times 3 and 3 times 3 and 3 times 3, which means it's a 9 times 9 times 9. And the cubic root is whatever number you multiply by itself 3 times, and that is 9. If you don't believe me, check it. Okay, check it with your calculator. Okay, so we have A is equal to 9. From here to here is 9. From here to here is 9. And the whole distance is 2A, and the 2A is 1 plus X. So 2A, which is 2 times 9, which is 18, must be X plus 1. Because I know in its closest approach, it's 1 astronomical unit, and its furthest approach, I don't know that. That's why I put it X. 18 is equal to X plus 1, so X must be 17 astronomical units. So this is the correct answer, but you need to check this one, and you need to understand what this answer means. Okay? The last one, calculate in the speed. And they tell you to calculate it in kilometers per second. So it's not in any units. It has to be kilometer per second. Of an asteroid in a circular orbit at 4 astronomical units divided by the circumference by its period. Okay. So they tell you to find the speed, find the circumference, and divide it by its period. They didn't give me the period. They give me the radius of the path, which is A, and A is equal to 4AU. I can find what P is using the fact that P squared is equal to A cubed, and A cubed is 4 times 4 times 4, which is 64 actually. 4 times 4 times 4 is 64. Check it again. So that means P is equal to the square root of 64, and that is 8 actually. So it's 8 years. That is the period, but I need the circumference. Since I have, this is a circular path, it's a circle, okay? And this is, it's A, which is the radius actually of the circle. The circumference is equal to 2 pi times the radius. So the circumference for the velocity is going to be 2 pi times the radius is 4 astronomical units, divided by the period, and the period is 8 years. 8 and 4 and 2 will cancel, and I'm left with pi, which is 3.14 astronomical units per year. But that's not what they asked me. They asked me in actually kilometer per second. I know 1 astronomical unit, and this is part of the quiz, by the way, 1 astronomical unit was 150 million kilometers. So that fixes this unit. I need to know the year. Well, 1 year is 365 days. Every day has 24 hours. Every hour is made up of 60 minutes. And every minute is made up of 60 seconds. So this is 1 year and how many seconds it has. So all I have to do is multiply these numbers by themselves and I find how many seconds in a year. Then the velocity would be just 3.14 times the ratio of these two numbers in kilometers per second. So the velocity will be 3.14 times 150 million kilometers over 365 times 24 times 60 times 60 seconds. Plug in the calculator and you're going to find the velocity in kilometers per second as the question was asking. Okay, makes sense to everybody? Now, if it does not make sense to you, hopefully you will come back to this recording and then look at it again, work on it. If you still have any questions, please reach out to me. The point with the homework assignment is not an exam. It's for you to practice these things, to gain confidence in the knowledge that you're supposed to explore in this subject, and gives you more sense of what the numbers are talking about, because we can talk all day about series, the fact that it's between Mars and Jupiter, but unless you do this problem, you will really have a feel for it. You will have a feel for what we say when we talk about Sedna. You will have a feel of how fast things are moving. I mentioned kilometers per second, but that's actually a measure that is not on a daily basis. If you wish, you put it in miles per hour. 1 kilometer is basically roughly 1 mile. It's actually 1.6 miles is 1 kilometer. So you can use that conversion to convert to miles. But the main thing is, don't multiply 60 by 60 at the end in the denominator. It's going to find it in hours. Okay, that's all. So if you want to have a feel for it, because probably if somebody tells you, I was driving so fast, I got pulled over by the police officer, and he told me he was going to give me a ticket. I told him I was only doing 30 meters per second, which is a lot less what you're talking about, 90 miles per hour. Of course, they're the same number, okay, because of the conversions. So the point in here is sometimes numbers tell a much better story than anything else that you can talk. You can talk as much as you want, but the numbers at the end will have a clearer message than anything else. So I know we went a little bit more than usual, and hopefully you guys will have fun with this assignment, and also with the topics of this week. And if you have any questions, please let me know. Any questions so far? Thank you. Thank you for the guys who are on the chat. So I'm going to stop the recording.